Welcome. We learned about the conservation, laws of conservations and the conservation of mass. In this lesson, let's just apply what we learned. So let's use these principles and drive an equation, differential equation based on the laws of conservation, the conservation of mass. But in this lesson, we will do something new. We will not only drive the equation as we did before, we have this equation. So I showed you before like this equation, but I never showed you how to solve them. Like what is the solution of these equations? So that's the new part that we will be doing here. We will apply what we learned to drive an ordinary differential equation for contaminant phase from laws of mass conservation, and then we will solve it using a technique called like separation of variables. This is another technique called integrating factor. I'm not gonna do it. I have the material here. You can look at it. I don't want this to turn to a math course. If you want to learn this, it's very easy. You can learn it in your own. And then we will practice analytical solution of differential equation for FE exam. Yeah. So let's just look at analytical solution. So again, in this module, I'm doing the analytical solution. In the next module, I'll be doing numerical solution because some of these differential equation, like some of these, especially that some of what I showed you in the previous lessons, they don't have an analytical solution. You cannot solve them the same by using this laws of calculus that we learned, and then you have to solve them numerically. Yeah. And remember, analytical solutions, it could be either a closed form, as we will do here, or infinite series, and we did infinite series solution. Yeah. But let's do some analytical. Let's first drive the equation, do some analytical solution, and let's see what we have. Yeah. So here, let's just think about this. Okay. So I'll start the derivation very basic. Yeah. Uh, the amount of radioactive contaminant is a in not is in a closed reactor is measured by concentration. Uh, C, which is measured in becquerel per liter, okay, or BQ per liter. The contaminant decreases by a decay rate. So that's the decay rate K, where K is a decay constant like 1 over day. Derive the equation for the mass balance of this reactor and solve it. So you have this reactor. In this reactor, you have some concentration which is like keeps decreasing. Yeah, it's maybe something like this. We have like here, this is a concentration, and we have a decay rate. So this is concentration, and this is time in day. And here you have the concentration in BQ per liter. So we want to find this relation. We want to find the equation for this decay. So can we do this? We want to find the equation and solve it so that when we solve it, we will have a relationship like Q with time. Not just the rate of a change, but we'll have this relationship. Yeah. How Q is changing with time. So can we do this? Yes. Uh, so basically, like, let's just think about it. So we can say like at time t is equal to 1. Yeah. Initially, we had like C is equal to 1. At the second time, because C, the concentration is decaying using this rate, then we will have a different concentration. We will have C2. Yeah. Okay. Uh, so here, what we can do, basically, we can remember we can say like the concentration 2 minus concentration 1 is equal to the change in concentration, the rate of change in concentration. Yeah. And this has like a rate uh, constant, and that would be also this is This guy here will be also like changing in time. Yeah. So that would be changing from like time 2 to time 1. So that's basically the rate of a change. Yeah. This is a negative. Okay, so the rate of a change in concentration, like from T2 to T1, okay, is equal to how this concentration is decaying according to the rate constant. So remember this is the rate of a change. That's the whole idea. Remember, like derivatives are seeing the rate of a change. So that's basically the rate of a change, like the change from C2 to C1, from time 2 to time 1, like from time 2 to time 1, the change in C2 to C1 is equal to this K time the concentration that you have. Yeah. So we got something that looks like this. So that is like one way you can look at it. Yeah. So here we will get like dc over dt is equal to negative kc. And we remember that if we want to find like the derivative of this guy, so what we can do, we can say like the limit of dc over dt as like time goes to 0, like the instantaneous rate of a change. That would be equal to what? That would be equal dc over dt. So the instantaneous rate of a change dc over dt is equal to negative kc. So now we got a differential equation. Why? Because why this is a differential equation? Because we have a function c, which is a function of time, and its derivative, like here. So we have a function and its derivative, and that's the definition of a differential equation. Is this ordinary or partial differential equation? This is like ordinary differential equation. Why? Because it has one independent variable. Is this first order or second order? This is like first order. Why? Because we only have the first derivative of concentration with respect to time. Is this linear or non-linear? It is linear because the decay term here has c to the power of 1. Is this homogeneous or non-homogeneous? This is homogeneous. Why? Because we don't have any extra function of t here. Yeah, we don't have any extra function of t here. Uh, so this is a first order ordinary differential equations that's linear and homogeneous. And this is usually something that you can change. Yeah. But here, this is like the conservation of mass because this is like a change in mass, the change in mass is equal to decrease by dk. So the change of mass is equal to the decrease by decay. Yeah. So now we have an equation. Okay, so uh, I have like dc is equal to dkc. But this is not exactly what I want. I don't want the rate of a change. Like I want something like this. I want to find like concentration and time. So I want to see how concentration is changing with time, not how the rate, not something that looks like this, not this guy. I need to get something like this. How can I get something like this? To get something like this, we need to solve this equation basically. And so what I will show you is I will show you like how to this like first order linear homogeneous differential equation. How can you solve it by a technique called like separation of variable? In order to get a relationship between concentration and time, direct relationship, not in terms of derivative. Yeah. So here, this is the relationship like dc is equal to negative kc. How to solve this? We can use a technique called separation of variable. So basically, the separation of variable, I will like separate this guy, like the dt, from the dc. Like I will separate this guy from this guy. So let's do it. So here I will say like integration. And to solve this, you need to integrate because remember, like this differential equation, like how to solve it, you need to integrate. So I will say like the integration of dc is equal to dt. And then I bring this c here. So that would be 1, the integration of 1 over c dc is equal to negative k dt. So you see like what I did here? And then now that becomes simple. I just integrate, and that's again, see, so I integrate both sides, yeah? I integrate both sides. So that becomes simple because I just need to integrate like this guy and I need to integrate this guy. The integration of this guy, remember that is like len c. So I integrate this guy with respect to c, so the integration of 1 over c with respect to dc, that's like len c. And the integration of this guy, this is a constant, so I can take this guy out. That's a constant, negative k. So I can put negative k. And the integration of dt, okay, 1 dt, that is like t. So I got t. And then am I forgetting something? Remember, this is an indefinite integral, so I need to put a constant here. Okay. Wow, I got a relationship. So I got a relationship and let's just make it look a little bit nicer. That doesn't look nice. So let me just, what should I do? Let me take the exponent of both sides. So if I did this, so that the exponent of length c, that is c, and the exponent of this guy, that would be kt plus uh, sorry, that would be kt plus c. Yeah, here's the constant. Yeah, because like you take the exponent of this guy and the exponent of this guy. Yeah, so that will give you c, and that will give you something like this. And then can we simplify this further? Yes, so we can say c because like negative kt plus c, that is equal to e to the power c, okay, e negative kt. So I can simplify it like this. So here, this is the concentration. Oh, see, here's a little bit tricky because this, maybe, see concentration here. Let me make this a small c, yeah, because this is small c concentration and this is a constant, let's say. This is just the integration constant, but this is the concentration, yeah. So here, this is the integration constant, and this is the big C here. Remember, this is like E, this is just a constant, yeah? So I can just call this constant. I can give it any name, constant 1, yeah? So the concentration is equal to, because this is a constant. A constant could be anything, yeah? Is constant 1 E negative KT, yeah? So basically, I have here this relationship where I have like the concentration is equal, like I can express it as an exponential, like this decaying exponential function with time, and that's exactly what we expect. So we have this exponential decay. That's exactly what we expect. Like you have this negative exponential decay means that this c will be decaying with time, giving this constant here. See, this is a constant. This is concentration. This is a constant. Okay, so let's apply some uh, like let's say we can like let, for example, like let me just assume here at C1 we have like C node like initial concentration, whereas this is like C node that is like in the in the initial concentration at time equal to 0. Yeah. So basically at time equal to 0. So if I put like so at so I have C like C naught, and that is E minus K to the power 0. So I have like C is equal to C naught. Then I can express like C concentration as a function of time is equal to C naught, like my initial concentration at time is equal to 0, E minus KT. So now here, see this guy, yeah, this is a differential equation that I was able to derive based on the conservation of mass. This is the analytical solution of this guy. Let us assume, let me copy this here, try to solve it. Yeah. Let us assume we have a radioactive contaminant like tritium with an initial concentration, so C naught is giving initial concentration of Becquerel per liter, and decay constant, like decay constant is giving 0.01 day. Yeah. Then find the concentration as a function of time in day. I want to see like concentration as a function of time. So that is easy. Yeah. So concentration as a function of time. C naught, that's like 100. E to the power, that's the decay rate 0.1 T. So now I have an equation that shows me the decay of tritium is which is like heavy water, yeah, as a function of time. And this is very useful. Like this tritium, you can use it to study groundwater age, for example, yeah, and see if this is the young water or old water, and learn about the groundwater age, the transport, like how this water was transported, like the flow, sorry, of this water, how this water was flow from recharge until like the current point. You can So that would be the equation of the concentration decay of tritium, like heavy water. Okay. Then one thing you can do. Uh, okay, so now I have this is and like this is my final equation. I need to plot it. Before I plot this, let me just show you. Remember this solution here? We did this called like separation of variables, where like you separate the variables and you do the integration. There is another way of integration called like integration factor. I'm not going to do this because I mean, I don't want this to be like a math class. I think these details are not important for the purpose of this class, but here, if you want to look at it, you can look at it. But if you did this, you will get up with the same equations that we have here. You're going to get up with the same equations that we have here. But now we have, this is our equation. So this is the final form that we have, and we can plot it. So now we can plot it. Like we cannot plot this guy. Like we cannot plot dc over dt negative kc, but because this is just telling me about the rate of a change, how concentration is changing with time as a function of this decay term. But now, by integrating this guy, by solving this differential equation through through like integrating this guy, so like integrate this, you integrate this, yeah, by integrating this guy and solving through the separation of variables I did here, yeah. By integrating this guy, I was able to come up with this equation. Let me see how we are doing in time here, because I have one more problem. Okay, actually we are doing good in time. Yeah. So by integrating this guy, the c over the t negative equal to negative k c. So I was able to do like integration here using separation of variable, integration of 1 over c, dc is equal to negative k dt. Like by doing this integration, I was able to come up with this relationship, concentration as a function of time, and substituting. This is my initial value. So when we do modeling, we usually have initial condition and we have boundary condition. Here, so we have two things. We have initial condition. So this is an initial condition. This is a parameter or a factor. This is a parameter. So this is a model. Like in this model, this is a parameter of my model. This is the initial condition of my model. This is my dependent variable, and this is my independent variable time. Yeah, so the time is my independent variable. I can plot it, and then I can see the concentration picture in how it is decreasing from 100 to almost like zero in about 90 days. Yeah, and that basically will tell you something. This is very useful, as I told you. This serves actually as like this equation or this model like serves as a clock. Radioactive decays, this could be like a clock to estimate the age of groundwater. So basically, by measuring the current concentration of naturally occurring radioactive isotope like tritium, carbon 14 in groundwater and comparing it to its initial concentration or like the assuming start value for this concentration. So I know the assuming initial condition and I know how this is decaying with time. So I know this guy. Yeah. And then if I know this guy and I know this guy and I know this concentrations, then I can back calculate for times. Then we can estimate how long water has been in the subsurface. So we know the decay half rate. So I know like the decay half rate for this isotope, for this particular isotope. So each particular isotope will have like this decay rate. Then we can walk backward to measure the concentration and determine how much time has passed since water has been recharged. So this is important to know about like young and old groundwater. Like if we want, for example, this technique is used to learn about submarine groundwater discharge. We don't use deuterium, we use some light, like young isotope, like things that does not take like helium, for example. And then you will know about where submarine groundwater discharge is occurring and by how much. You can even estimate like the quantity of something like this, yeah. And this can inform us also about like groundwater sustainability because if we know how long does groundwater is staying there, how long for the groundwater is required to flow from one point to another, then that could help us to estimate what would be the sustainable abstraction rate, like sustainable yields that we can abstract this water and how long it will take it to like recharge again. Yeah. So these, yeah, so this is like if you took any course in, again, this class is a general class. We just review like what you need to learn from this class is the follow. Like what you need to learn from this class is how you come up with like the conservation of mass. From this conservation of mass, how can you develop a mathematical model like this? And then how to solve this mathematical model either analytically or numerically like this. And then once you do this, then how to interpret this, how to use this in field applications, that would be in other courses, that would be in contaminant transport course, for example. Yeah. So in contaminant transport course, that's where you will learn the field application of these things. Here you're just learning the general concepts behind the general concepts behind these, like developing these simple model. Yeah. Okay, so this is a practice problem. Let's see how we are doing in time. I think we are doing good. This is a practice problem, and I want you to just try to solve it in your own. It's asking you for the same thing to drive differential equation, something similar to this, and then you solve it, and then you answer this question. And if you answer this question, that will help you to understand that you understand much. Like if you can solve a problem like this means that you understand much because you understand the conservation of mass, you understand how to formulate a differential equation and how to solve it on your own and answer simple problems like these ones, yeah? And then you understand the mathematical basis or mathematical fundamentals for these types of problems. So try to solve it in your own, and I will do this in the tutorial session. I will solve it like step by step, and here is the solution. And this is basically the solution for this equation. And if you can solve this, then you can do your homework because your homework problem is exactly the same as this guy. I just like changing these numbers, like this is zero point 0.2, this is 0.3, okay, something like this. But you need to solve this first because in order to solve your homework, you need to solve this first. You need to understand this first. If you understand this much, so I think you've learned a lot from this course because now you know the mathematical principle, fundamental mathematical principle behind all these physics-based models that we develop. Okay, and now you were able to apply it on your own. Then if you saw a similar problem, you will be able to do it. Okay, so that's I think all for this lesson, and I think we are doing good in time, and I will